last speaker today is Kailis. This presentation started without him, that's all right. He's supervised by Michael and myself, and he'll be talking about the design of echo-state networks for time series analysis tasks. Go to the
Okay, so yeah, I'll be talking about echo-state networks. So firstly, to explain what an echo-state network is, to try and contextualize my research. So an echo-state network falls under the umbrella of reservoir computing, which is a machine learning technique where you have a recurrent neural network that is used to map an input to a high-dimensional space, and it's subsequently trained to produce an output. And compared to other techniques, it has a computational efficiency, and there are many varieties and different types of implementations, both physically and as simulations, and the original and most commonly researched type is the echo-state network. So to explain what an echo-state network is, each state in an echo-state network is defined by an activation function, which is non-linear, typically a sigmoid, such as hyperbolic tangent, which is then applied to the input signal, which is U in this case, the previous state of the reservoir, and then there is a bias term. So these matrices W that are listed here the first one is the input matrix, which scales the input to the higher dimension of your reservoir. The adjacency matrix, which defines the neural network, and then the bias. And all of these matrices are randomly generated, and the input and bias are usually generated using a normal distribution, and the adjacency matrix is typically generated as an Erdos-Renyi graph. And as a result of this activation equation, echo-state networks are dependent upon their most recent states, and this is the echo-state property. And these states are collected in state matrix, which is the capital X down the bottom, and then they're trained to the output Y using linear regression with regularization to prevent overfitting. And the fixed nature of the network and the linear regression is where sort of the computational efficiencies lie. So this is a sort of schematic representation of what's going on, where you can see the input that's scaled using the input matrix to the reservoir, which is your neural network, and then sort of the training process to your target. So taking a different step to embedding, which stems from Tarkin's theorem, which is saying that if you have a compact manifold and you have a continuously differentiable flow that defines an attractor, that the attractor can be represented in a higher dimensional vector of a time series arising from the attractor. And that leads to time delay embedding, which is a common form of embedding, where each form of your embedded vector is delayed relative to time, with the dimension being at least 2 times the dimension of the manifold. So the form of the embedding allows us to understand more about the dynamics of that original attracted system. So with the example of the Lorentz system of ordinary differential equations, on the right-hand side, the left-hand side, you have the attractor with the typical butterfly wing shape, looking at a singular dimension time series. You don't necessarily see the dynamics, but once you embed it on the right, you can see the double wing shape, and that's with a suitably chosen dimension and lag. So the form of a time delay embedding is similar to the form of the states of a reservoir computer, and that leads to the application of echo-state networks to time series analysis to understand more about the dynamics in the same way that time delay embedding can be used. So that was proven by Alan Hart in 2020, and he showed firstly that echo-state networks in fact produce an embedding, and that embedding is topologically conjugate to the dynamical system, which allows us to use it for dynamical systems analysis. And that leads to reservoir time series analysis, which is the use of the echo-state network for that purpose. And Braden here at UWA has spoken or published his PhD on this, and he has introduced a few tasks. Yeah, soon. Signal distinction, which is about separating between 2 different input signals, recurrence analysis, and then concept drift detection. So this leads to my research, which is to investigate how changing the parameters that define the reservoir affect its performance in echo-state networks. So parameter changing and parameter optimization is a key part of echo-state network literature, and it's suggested that different parameters can be used for different tasks and it will result in different performance. And these parameters haven't really been tested within the unsupervised context of reservoir time series analysis. So I'll be looking at the spectral radius, which is the maximum absolute eigenvalue of the adjacency matrix, the reservoir size, so the number of nodes in the neural network, and then the network type. So I initially introduced the Erdos-Renyi graphs, but we look at another type of graph, the scale-free network as well. So how we do this, we take the task of signal distinction. So you have 3 different input signals. So you have a base signal, a reference signal, and a comparison signal. So the reference signal and the base signal are the same, and the comparison signal is different. You drive the reservoir with these 3 signals, and you calculate features based on the characteristics of the node and the reservoir itself. And then you compare the values of these features with one another as a means of distinguishing between the signals. So in the diagram here, you can see the reference distances in the blue, which is the distances between the features derived from the reference signal and the base signal, and then the comparison, which is the comparison distances with the base distances. So you expect that the comparison distances are going to be larger than the reference distances because it's different from the base signal, and you can calculate a score based on that, which is the number of trials for which the comparison distances are larger than the reference distances, and we can kind of form a probability that, like in a frequentist manner, that the ESN is able to conduct signal distinction. So the number of trials for which the comparison distances are greater than the reference distances indicates sort of a probability that the signal distinction task works. So the reservoir features that we use to do this, we use the mean, which is the mean of the nodes in the reservoir over time, and then the covariance, which is how they change with one another. And then there are trained features, which are the auto readout values, which are just the values in the W out matrix that I introduced. One-step readouts, which are when the reservoir is trained to the input signal at one time step in the future. So you're predicting with some sort of shift of one time step. And then reservoir complexity, which is derived from those readout values. So if you take the absolute value and rank them by magnitude, you can produce a plot like this, and it calculates the area under the curve. So the idea behind that is more complex signals will require higher magnitude reservoir output values in order to model them, because you're using a linear combination to model them, and you will need more nodes to more accurately model something that has more complex dynamics. And there will be more nodes used, and those nodes will be of a higher value, and hence there would be a higher area under the curve to formulate the complexity feature. And the inputs that we looked at were the Lorentz system and the Mackey-Glass equations. So these systems exhibit both stable periodic regimes and chaotic regimes, and we aim to compare and distinguish between time series from these different types of regimes. And so in terms of our parameter variation, we are changing the spectral radius in our first trial up from 0.1 to 4. So looking at a range of spectral radius values and seeing how that impacts upon performance of the signal distinction task. Then we vary the reservoir size, and we're more interested in lowering the reservoir size because of this issue of computational efficiency. So the size of the matrices you're dealing with are determined by the size of the reservoir. Larger matrices are harder to compute with, which restricts the size of the time series that we can work with. And ideally, we want to work with larger time series. So seeing at which point limiting the size of the reservoir impacts the performance is our motivation there. And then for the scale-free network, we use the Barabasi-Albert algorithm with sort of preferential attachment, whereby we have some nodes of higher degree that act as sort of hubs, and then they're surrounded by these lower degree nodes, as sort of seen in the diagram, in comparison to the Erdos-Renyi random network. So to our results. So this is for varying the spectral radius with respect to the covariance metric. So we can see that for the lower spectral radius values, there is distinction between the reference, which on the left is the comparison, which is a chaotic time series from the Lorentz system. And then in the orange, we see a periodic time series from the Lorentz system. In the green, another chaotic Lorentz time series, and then in the purple, the Mackey glass system in chaotic regime. So with the increase in spectral radius, we see more of an overlap between these density plots, less of an ability for the ESN to distinguish the signals. And looking at the summary scores in the bottom corner, we see that around 2.4, there's this steep drop off in the scores where the performance for the echostate networks really drops off. So this was repeated throughout the features, and it's due to the nature of the spectral radius and what it controls. So the spectral radius is responsible for the echostate property and the extent to which successive states are determined by their previous states relative to the input signal. So when the spectral radius increases beyond around 2.4, the states are too much determined by the previous states and the input signal is forgotten, such that the dynamics that are present in the input signal are no longer modelled and that the distinction cannot be made based on these characteristics. And that's sort of referred to as the edge of chaos, and is the point where subsequent results aren't very useful to us. And like another way of thinking about this is that the spectral radius pushes each of the nodes the limits of the activation function. So because it's a sigmoid, it tends towards these limits, -1 and 1, and you can't necessarily distinguish between the characteristics of two nodes of higher value. So onto the next test of varying reservoir size. So this is for the auto readout, which is one of the trained features. So we see that for increasing the reservoir size, that we have an increase in the performance of the reservoir. And this is in contrast to when we're using the mean, which is one of the node characteristic features. So with the mean, there isn't necessarily the drop-off in performance with the change in reservoir size. So the reasons for this would be because the reservoir size is concerned with the training of the features, because as I said, you're trying to construct the target using a linear combination of values from those readouts. So the value of the readout is more important in constructing that representation, and with more nodes you're able to construct better model for your trained output. Whereas for those node characteristics, it doesn't necessarily matter how many nodes. Even with one node, you would be able to see statistical change in the system. You might not necessarily see dynamical change, but if there's statistical change, that can still be picked up regardless of necessarily how many nodes there are. And with this trial, we chose to generate a new reservoir because when we're removing the nodes, the connections between the nodes are going to change. So in order to standardize for that variation, we regenerate the reservoir each time. So into scale-free networks. The scale-free networks generally exhibited similar behavior to the original Erdos-Renyi graphs. So you can see the drop-off, slightly different value of spectral radius, but the general trends remain, and that was, I guess, useful in determining that scale-free networks worked. They had been used a few times in supervised learning tasks, but never in these unsupervised tasks, and I guess the performance is interesting and allows us to see the impact of some clustering on the performance. So to understand sort of what's going on beneath the hidden layer, we find that some of the nodes in the scale-free network have high variance between that -1 to 1 range, and then there are some that stay very close to either -1 or 1. And we propose that the nodes that are staying very low to -1 to 1 have -1 or 1 and have low variance, that they're not so much responsible for the information that leads to the embedding. So we show that by plotting the variance versus the degree. So those high degree nodes are seen to have lower variance and are less responsible for the information that leads to the embedding. So the idea behind this is that the nodes with a large number of connections are overwhelmed by their neighbouring nodes in a similar way to high spectral radius cases, such that they forget the input and are more and more determined by the neighbours and not the input itself. And this is exacerbated when we increase the spectral radius because there's a combined impact of increasing the spectral radius on the effect of what the nodes are activated to be, and these high degree nodes with their large number of connections. And this trend is also seen when you're looking at the readout values. So the higher readout values, which are more responsible for producing the linear combination that leads to the embedding, come from the nodes of lower degree, and then the nodes of higher degree have smaller readout values, said to be less responsible. And again, that's sort of exacerbated when we increase the spectral radius. So to our conclusions, we've demonstrated that what the impact is of changing the spectral radius, that it increases, that as the spectral radius increases, it sort of decreases the ability for the echostate network to accurately perform the task. This is in line with what we would expect, but it hasn't been shown in an unsupervised context before, so that's where the interest lies, and it can help us to make reservoir time series analysis a more robust field of study. But in general, hyperparameters should always be tailored to what you're doing, what the characteristics of the input are, and the task that's being looked at. And in terms of future work, it would be interesting to see how adding noise to the signals impacts the ability for the signal distinction task to be conducted, and how changing the hyperparameters might impact upon that. And again, looking at it in the context of different time series analysis tasks beyond signal distinction. And then in terms of the scale-free networks, looking at other node characteristics apart from degree in determining how important certain nodes are to help us with potentially removing nodes to aid in the computational efficiency that I discussed. Thank you.
Who's got questions?
Devon?
You go first.
Oh, does someone else want to?
Sure.
You go first.
Okay, cool. So I may have missed the answer to this because you might have said, you're talking about like high variance nodes and low variance nodes. Does what's a high variance node or a low variance node vary with the input signal?
What those specific nodes are, like for a more...
We kept the same reservoir, but we changed the input signal.
Yeah.
Would you typically find with the high variance nodes and the low variance nodes stay the same? Or?
So like those individual nodes might change, but it's like the proportion of nodes that are necessarily high variance or low variance didn't. So because the amount of variance was more determined by the degree rather than what the input signal turned out to be. So the proportion of nodes that were of high or low variance didn't change.
So the proportion changes, but you think the actual nodes will change depending on the type of input signal?
Well, the variance was more determined by the degree of the nodes rather than what the behaviour of the input signal.
That was just a mistake.
Yeah. So the Hart embedding is just the theoretical basis for reservoir time series analysis. So proving that echostate networks provide an embedding allows us to apply echostate networks to time series analysis. So it's not necessarily related to what I'm doing, but it's sort of just in terms of background tells us why we can use echostate networks for time series analysis, because you proved that it was an embedding. Well, they guessed that it was an embedding because of the form of the state vector, like compared to delay embedding. So there was a strong supposition, and it was even proposed by Jaeger when he introduced echostate networks, but had not yet been proved.
We'd been assuming it was a delay embedding. The Hart work's interesting because he actually put it into a formal proof and then showed it. Yeah, the idea that your reservoir computer generates an embedding is sort of underpinning a lot of this work. The structure actually analysing is not some machine learning thing that we don't understand. It's actually just a different form of embedding, and understanding how that embedding works in response to hyperparameters like Lucas has looked at is then important in terms of using it for generating liquid embedding.
Like most ones, proves that you can do it.
Got a question. I understand why you want to check the effect of spectral radius as the result of whatever task it would be. That makes sense. What's not quite clear to me is what is the motivation of doing like a scale-free as opposed to Erdos-Renyi, when you have recurrence, both cases you'll have recurrence, right?
Yeah.
So like,
Um,
missed that part. Why you?
well, like, there's not really a massive like difference in performance. So it's more to do with like removing the nodes. So if the nodes have different characteristics, instead of removing them in sort of just a random manner, if we can remove nodes of different type and see what the impact is. So it's more of like an interest, and the fact that it hadn't been applied to unsupervised learning. It's not really, I guess, that important, but it's more just seeing the impact, because scale-free networks have been introduced in ecostate network contexts, and seeing if there would be different performance, because there had been some different performance in the supervised context. So.
Any other questions on content?
Back to the provided edges chaos. Was it for this one? Yeah. What was the reason why when it goes over the circular road before? What was the? I must have.
So the states of the reservoir at that point become more and more dependent on the previous states of the reservoir rather than the input signal. So the input signal is forgotten, so to speak, so then the dynamics aren't preserved, and it's not present within the output.
You still felt like saturation on the.
Yeah, so the signal, I guess, is the reservoir is, I guess, being saturated by itself, by the previous states, rather than taking information from the signal. So the signal is no longer relevant in the mapping that the reservoir produces. Yeah, I agree. Is that? So like the spectral radius comes from the adjacency matrix that defines the connections between the nodes. So when the spectral radius increases, then like that matrix has far more weight in the initial activation equation.
I think I think if you take rho even larger, it sort of becomes stable again, and you get the switching code. I'm not sure if the saturation of the signal is what's caused it to be chaotic, as opposed to just you're pushing things past each other as opposed to pushing them together.
Yeah, I'm not sure. 4 is like quite very high, much higher than anything that's really been tested, sort of like an extreme case. So I'm not really sure. Like most of the discussion around spectral radius in supervised context talks about values less than 1 being ideal, and then kind of ignores really talking about high values, because I think it assumes that it's just going to corrupt the signal. But yeah.
Yeah. You saturate it and it starts switching based on the input signal. But then you lose some memory from the internal dynamics. Or I think something like that can happen if you take spectral radius really, really high. You might also need to take the input scaling high as well. It becomes stable again.
You need to be increasing your input scaling as well. Because otherwise the input's going to be this really tiny value.
It's more the ratio of the spectral radius to the, because the spectral radius is like a gain of your recurrence, right?
Yeah.
So it's just more like the ratio of the
This is
spectral
how
radius
the
to your
questions
gain.
get open. So you just let the audience answer.
You also get back to can you just tell me what these plots?
Um,
I know so funky, what are they doing?
So they're densities of the distances between the features from the different signals. So on the left-hand side is the reference signal, which is drawn from a chaotic portion of the Lorentz time series. Then in the orange is a stable periodic portion of the Lorentz. In the green is another different chaotic Lorentz time series, and in the purple is from the Mackie glass system in chaotic regime. Yeah, so the width of I think they're called violins, is the density and then like the vertical is the spread of distances.
It's sort of like a funky box plot that actually tries to show you what the densities look like.
Are there labels for the colors?
Like there have been in different versions of the plots, but it looks too small in and too cluttered on the page. So in my thesis, it's like described in the figure caption, like from left to right is this, but it's something that we're changing around.
Yeah, you should stick somewhere on this figure, even if it's just text, blue text, reference, orange text, periodic,
Yeah.
green text, whatever. So,
Yeah.
that was my number one.
Well, with that, we will look at comments on the presentation. In terms of time, it was 16.5 minutes, so you've got a bit more to work with there.
So I said again, how long?
16.5 minutes, so you have a bit more time
Yeah,
there.
it's much quicker than every time I've done it at home. It's been longer.
My biggest comment is actually this.
Yeah.
Just top of my
You had,
page as
you had a
well.
whole heap of content, you had all the words were there, because I knew what you were talking about, I could follow all the words. But especially for the, up until about slide 13, we were off at the races.
Yeah.
Just like, very quick. Just, unsurprised all three of you. Two of you. Yeah, two of you. If you stop halfway through your sentence and just take a breath, no one's going to notice. And it will slow down, give you a chance to explain stuff. That 2-second pause, no one thinks that you're suddenly having some sort of memory episode or anything frozen. Will just help make work.
Yeah.
Make it quite easy. It's easy to do. Label the axes. I was also just going to say the questions. You kind of jumped out a bit in your answers. So particularly, you let Shannon bully you into, when Shannon was asking about the embedding, heart embedding, and you sort of turned and said, well, actually it's not relevant, but stick to your guns. You know what you're doing. So it is important. It is relevant. And you then went and said why it was important, and why it was relevant, and why it was what you were doing.
Yeah.
But, sort of in general, though, probably a little more about what we're actually doing and why it's relevant. Particularly with like introducing the embedding stuff and all the stuff we talked about early on, kind of was just there. It wasn't necessarily clear why we care about it. Like the embedding was sort of the big one there, but also we talked a bit about the one-step predictions, like how we actually train a reservoir computer, but we didn't actually talk about these are machine learning models. We're using them for supervised learning tasks typically, and what you're trying to do is help move it away from that. So sort of a bit more explanation of why we're actually doing this is probably missing a bit from the slide.
And on the first part, when you use the items there, on the first 13 slides, I think you got all the words out. I'm not sure that you got them out in the right order, defining what practice theory actually does. I don't know, Devin, were you listening carefully?
I read it.
So if anyone was actually listening to what you actually said and actually knew what it was, more a little bit confused. So just make sure you know what you're saying.
Yeah.
That's a really minor thing. There's probably about outside of this room 4 people in Western Australia who care about that. Unfortunately, 2 of them will.
Anyone else got another point? Otherwise, I'll
Yeah, you talk about like why you're doing that. Actually, I think you also need to emphasize like what you're doing as well. Is to start like what is happening with this reservoir time series analysis. You know, you've got this big function generator, it's going to process my time series and I'm going to look at key indicators from it and really emphasize that. Because again, I think it's probably applies to everyone. Like the audience is going to be much more varied than it is here. So it's sort of the whole reservoir.
Yeah.
So sort of on that, spectral radius, reservoir size, hyperparameters, they need to be introduced.
Yeah,
Or-
I plan on doing that. I completely, yeah.
On the if you go to the very first slide, Wait, like the very, very first slide with text, even earlier. Yeah, that one. There's a lot of words on there that I think, depending on audience, like even this words like recurrent neural network, hidden layers. I'm not sure if the audience will all know, but like explain it later on. Maybe
Yeah.
bring that later.
And you did actually kind of explain these words at this point, but again, we're going very fast.
Yeah.
Yeah.
And you don't have, take your point, Eugene, but you don't have to, you can leave some of the words up on the slides just for people that know what they mean.
Yeah, like I guess it's not really relevant that there is recurrence or anything. I guess, yeah.
But yeah, just to try to make sure that, think about what you're putting up and whether it's necessary to explain what you're actually doing.
Yeah.
My last thing was the equation of the help me out here. Is this a notation that people use with W's everywhere? Or will you call everything a W?
No, typically we like V, W, and B most of the cases. I know I have used all W's in my thesis just because I was very limited on the number of variables I still had available. So every matrix in an XZ network was V, and the superscript changed their meaning. So actually B is
There's W for weight.
Yeah.
Although actually, no, sorry, W and W, no, that has been used before somewhere.
Yeah, it was used in the original. It was used in the original paper.
W's
Yeah.
been used.
Okay.
Yeah.
Might be worth repeating the equation of the
Yeah.
The one thing that you do need to add to this slide is to put it right in that UT is the input, ST is the state.
Yeah.
Well, potentially you swap out the reservoir training with that on a different slide when you picture on this slide.
Oh, the reservoir training is just there. It's a fancy equation.
Admittedly, I would probably take the training part out of this, put the diagram here, and then actually talk about the training and the supervised part separately as this is what they have been used to, because then that sort of sets up the conversation later on of we're not doing this explicitly, we're doing something else as an option.
Yeah.
I think generally, it's not very clear which bits of what I'm doing are things that we're doing and which bits of what we're doing are just things that other people have done.
Yeah.
And this is setting up at the beginning. So people do this, we want to do this. Just because there'll be people in the audience that are trying to figure out what did you actually do? What's the value of that?
So would it be worth like explaining my aims more concretely before I introduce even what echo set networks are? But like I feel like they wouldn't necessarily make sense.
You can introduce it to echo set networks, you can do the background, and you can say, what I've worked on this, what I've been doing this year is this.
Yeah.
And Sarah did again at the end.
Yep, say it at the start. Say what you're going to say, then say what you're going to, then say it, and then say what you just said.
Yeah. Your Jason as well, and make sure you have a nice concluding slide and actually bring it all together. I think one of the other two didn't have that, and that I think is a very important thing just to make sure you do sensitively summarise for the people who zoned out for the rest of the talk why it matters.
This is the executive summary at the end of what you just missed because you spent through the last 20 minutes.
Yeah.
Yeah, it's.
Alright. No other points there. Let's thank Lucas one more
Thank you.
time. And all that. Yeah. Next week is the colloquium. Yeah, we do have two other honours students who I'm currently chasing up to find another time for them to be able to do it. It might be during the morning keys if we can't organise a single week, because I think there's only 1 week after the colloquium before you guys have to do your actual presentations. Oh no, it's 1 week. The week after that, thesis is due. said they didn't want to do that at all. I think we'll be after that in the presentation.
It's also important to grow.
Oh, you're invited. Complex systems morning tea, Thursday, 11 a.m. every week in tea week.
Okay.
Yeah.
I won't come in the wall. I'm going to have these talks.
Yeah.
Yeah.
Yeah, it'll be there. What was I gonna say? Oh yeah, so these talks have been recorded.